One thing that's been part of the vast majority of cars since the first of the horseless carriages is me. I'm the internal combustion gasoline engine. You may think I'm an antique and that I ought to be retired. Well, R&D, you know, research and development, have been trying to replace me with turbines, electrics, steam, and even my cousin the diesel. But I've kept on improving so well that I'm still going strong. More efficient, more economical, producing more power and better mileage, and less pollution. Yet, basically, I still work the way I always have. To begin with, as most of you know, I used to mostly drive the rear wheels. But more and more, you'll see me sitting sideways and driving the front wheels. This transverse front drive gives the car better road traction, great for snow or slippery conditions. There's no long drive shaft to the rear with its floor hump, and weight is saved. And higher miles per gallon, plus emissions control, are prime concerns of automotive engineers. Along with economy, I still have power. My power starts here with my pistons. They're not very big, and they don't move very far up and down, only about 3 inches. And they never move this slowly. When you're driving out on the highway, they go even faster than this. Each piston goes up and down as fast as 80 times per second. That's right, I said 80 times in 1 second. In that small 3 inches of travel, each piston starts up from a dead stop and reaches a speed equivalent to 50 miles per hour. Then comes to a full stop at the end of the stroke and does it over and over 80 times per second. And that makes my power. I'd like to show you how I do it. Let's begin with a cylinder. This one is closed at one end, like a cannon. Put in a charge of gunpowder, pack it tight, then the ball. Ignite it. Power. Now, look at me again. Give me a piston. That's also a cylinder with one end closed. It has rings to make it fit snugly and hold pressures, and to keep the cylinder wall clear of oil. Put in an explosive, a mixture of gasoline vapor, the fuel, and air. I compress it, and then use a spark to ignite the mixture. It burns quickly, expands, and pushes the piston down with great force. Coming up, I drive out the burned gases and start the cycle over again. Intake, compression, power, and exhaust. I work a cycle of 4 strokes of the piston, which makes me a 4-stroke cycle internal combustion engine. Now, to turn the wheels. Each of my pistons has a large pin that links with a connecting rod. Its lower end is connected to the crankshaft. As the piston moves up and down, the connecting rod causes the crankshaft to turn. You can see my power action in the cylinder is straight line motion up and down, reciprocating. The connecting rod and crankshaft change it to rotary motion, which is what I need in order to turn the wheels. My designing engineers put a circular weight called a flywheel on the crankshaft. It smooths out my power stroke and carries it through the 3 non-power strokes that are part of each cycle. I have 2 valves per cylinder. These are called the overhead type, because that's where they are. The intake valve opens to let the fuel and air mixture in as I start the intake stroke. The valve closes for compression and stays closed during the power stroke. The exhaust valve opens after the power stroke ends, so that I can drive out the burned gases during the exhaust stroke. At the bottom of the stroke, the cylinder space has a certain volume, the space for the fuel and air mixture. Say it's 56 cubic inches. As the piston rises, it compresses the air and fuel mixture into a very small space, say 7 cubic inches. That means I have a compression ratio of 56:7, or 8:1. The fuel and air mixture comes from my carburetor, or from a fuel injection system. When I'm fed by a carburetor, my fuel pump puts the gasoline into the carburetor bowl. A float shuts off the inflow, preventing overflow. The bowl is connected to a tube with small openings at the tip. As the piston goes down, it causes a stream of air to be drawn in through the air cleaner and down past the tube, drawing a fine spray of gasoline with it. The gasoline droplets quickly vaporize as the mixture of air and fuel goes to the cylinders. The throttle valve, operated by the accelerator, controls the amount of mixture entering the cylinder, which controls the power I develop. Like a carburetor, an electronic fuel injection system has an accelerator-operated throttle to control the amount of mixture entering the intake manifold and cylinders. But the gasoline is injected into the throttle body in pulses of very precisely timed length. Long pulses enrich the mixture, and short pulses make it lean. The best pulse length for a given driving condition is computed by an electronic control module. It's like a brain for me, continuously gathering information and calculating the best pulse length. With the help of sensing devices, the module monitors the position of the throttle, the engine speed, taken from the distributor or spark control, my intake manifold pressure, the amount of oxygen in the exhaust stream, my coolant temperature, and several other factors. Pulse length is changed for acceleration, deceleration, cold starting, altitude, whatever calls for a change in the mixture, the ratio of air to gasoline vapor. That's TBI, throttle body injection. Another kind of fuel injection, called port injection, gives each cylinder its own fuel injector. A computer usually controls the operation of each injector and the time length of each pulse. No wonder I'm still going great, with modern fuel delivery systems making me more efficient. Whatever the system, the mixture has to be ignited, which is why each cylinder has a spark plug. To fire it, my battery or alternator, low voltage, is boosted to high voltage by an electric coil. It creates the spark. The time when this happens is handled by my distributor or by an electronic spark control. The distributor shaft is geared to the engine so that the electricity is switched to the proper spark plug at just the right moment. But before I can be a practical engine, I need a few more parts. One is a block, usually cast iron, or sometimes aluminum, which may have the cylinder holes lined with sleeves of iron or steel. Then there's my head, more like a cap, really, fastened on tight enough to keep me from blowing it off when the pressures inside go up. Underneath, a removable pan holds the oil I need for lubrication. I also need a mechanism to open and close my intake and exhaust valves. That's my camshaft, geared to my crankshaft by timing gears or belts, so that, like the spark, the valves will operate at the right times in the cycle. The camshaft turns once, while the crankshaft is turning twice, because the valves are operated only during 2 of the 4 strokes. The cam system operates a mechanical or a hydraulic lifter, push rod, rocker arm, valve, and spring. With each turn of the shaft, the cam pushes up the lifter and the push rod, raising the rocker arm so that the other end pushes down on the valve, opening it and compressing the spring. When the cam turns away from the lifter, the action reverses, and the spring holds the valve closed tightly. Some members of my engine family use an overhead camshaft, which eliminates push rods and rocker arms. A large chain belt or a gear drive turns the camshaft. My intake manifold connects the carburetor and the intake valve, and my exhaust manifold takes away the exhaust gases. So far, I've shown you just one cylinder. Engines have more, of course. Here's a four-cylinder engine. With the cranks placed at different points on the crankshaft, the power thrusts are evenly separated. There are six-cylinder engines, eights, fives, and maybe threes someday. My V6 version is a pair of three-cylinder blocks. A single crankshaft takes the power from both sets of pistons and connecting rods. The V8 is similar, with two four-cylinder banks. I have a cooling system to keep my various parts from overheating. The system is basically a water jacket, really just a space in my block and head through which a coolant flows, water with antifreeze or anti-corrosion fluid added. Hoses connect the jacket to my radiator, which is made of a good heat-conducting metal with spaces that allow air to flow through. Usually, a water pump and fan, together on one shaft, are driven by a belt, which in turn is driven by a pulley on my crankshaft. The pump circulates the coolant so that it absorbs engine heat, and then goes to the radiator, where the outside air carries away the heat, cooling the coolant, and the cycle continues. The fan helps to keep outside air flowing through the radiator when the car's not moving. On cars with automatic transmissions, there's a small separate section of the radiator that cools the transmission fluid. The fan on a transverse engine in a front drive car is usually powered by a small electric motor, which operates only when it's needed. I have to have a lubrication system too, otherwise friction would quickly burn me right up. The system includes the oil supply in the oil pan, an oil pump, and small pipes and channels that carry the oil to all my moving parts. The pump circulates the oil through the main bearings that support the crankshaft, then through passages inside the crankshaft to the connecting rod bearings. Oil also goes to the camshaft bearings. The cylinder walls have oil splashed on them as the cranks hit the oil in the pan. The circulated oil, which serves to keep me cool and clean and lubricated, drops into the pan for recirculation. It seems like I'm a big bundle of systems. Lubrication system, cooling system, valve train, fuel and ignition system, and more, pollution control systems. One is the catalytic converter, a chamber in the exhaust line between the engine and the muffler. It converts the undesirable emissions, changing them chemically into harmless substances. But the active materials in the converter will be made ineffective by leaded gasoline, which is why your new car carries warnings: use unleaded fuel only. You've probably heard of the PCV system. That's positive crankcase ventilation. The crankcase of any engine accumulates a certain amount of blow-by gases, unburned and partially burned gases that go down past the pistons. With PCV, the blow-by gases are drawn up through the one-way PCV valve and into the cylinders, where they're burned. PCV has totally eliminated air pollution caused by crankcase emissions. Another anti-pollution system is CCS, Controlled Combustion System. The hot exhaust manifold is used to heat the underhood air that enters the air cleaner, resulting in more complete burning of the fuel and air mixture. The mixture can thus be set leaner which, combined with other measures, reduces the amount of hydrocarbons and carbon monoxide in the exhaust. Another system, called the air injection reactor, or the air management system, is a kind of exhaust afterburner. An air pump, belt driven by the engine, forces a stream of air into the exhaust manifold, where it causes most of the unburned hydrocarbons to be burned before they reach the tailpipe. The evaporative emission control system traps fuel tank and carburetor gasoline vapors in a canister when the engine is not running and burns them up later in the engine. How do I keep track of all these systems and know they're operating at their best? Not to worry. The computer command control system has come in to take over. The brain of the system is an onboard electronic control module, a microcomputer, slightly larger than a paperback book. It gathers data, analyzes it, and makes its calculations at the rate of 300,000 per second. The system can monitor up to 15 different engine and vehicle functions, and can control as many as 9 operations, thereby helping to maintain my good fuel economy and the drivability of the car, in addition to lowering exhaust emissions. Yes, I've come a long way in my long life. I've survived against efforts to replace me, thanks to technological advances and tough competition. I think I'm still the best type of automobile power, with my increasing efficiency, higher and higher mileage out of every drop of fuel, virtual elimination of undesirable emissions, and by my making car driving easier and more reliable. The cars know. They tell me, you're not getting older, just better.